It has always been a hope of mathematicians that all of mathematics could be founded on a finite set of simple axioms. In the early 1900s, it was believed by most that the theory of sets would accomplish this. In fact, the logician Kurt Gödel in the 1930s demolished any hope of founding mathematics on a finite set of axioms with his remarkable theorem that in any system of finite axioms rich enough to give us the natural numbers, first of all, one will always find statements that cannot be resolved as either true or false. And secondly, one can never prove that the axioms will be consistent. That is, they may lead to contradictions. We will never be certain. In spite of this daunting news, most mathematicians and scientists just keep proving results in pure mathematics or keep using mathematics as a tool for modeling nature. In particular, we still use set theory as a fundamental tool. A set is just a collection of objects. These objects are called elements or members of the set. We insist that membership in the set be defined by an unambiguous rule. For example, we can talk about the set of even natural numbers. In this case, the number 2 is a member, 3 is not. Our rule for membership is clearly unambiguous. Another example is a set of all points in the plane with both coordinates odd natural numbers. Then the point 3, 6 is not a member, but the point with coordinates 3, 5 is a member. Or we could consider all students registered in a particular course whose last name begins with a W. Again, the rule is clear and unambiguous. Well, as unambiguous as determining a student's last name. Notice that in each case we seem to have unconsciously assumed a universe in which we are operating. In the example of the set of even natural numbers, the universe could be all natural numbers. In the example of points in the plane with both coordinates odd, the simplest universe is the set of all points in the plane with both coordinates natural numbers. Although it might just as well be the set of all points in the plane, we really didn't carefully specify our universe. In the example of students in a course, the simplest universe is the collection of all students registered in the course. In this case, we were again careless about specifying our universe. In general, we don't worry too much about the universe when we are specifying sets in mathematics. Only when we are dealing with logic or the theory of sets itself do we need to be careful about the universe. One useful notation for a set defined by a rule R is to put brackets around X vertical bar, meaning such that X satisfies R, and call the set A, for example. If an object belongs to A, we write X with a sort of a big epsilon A. If an object does not belong to A, call the object Y, then we put a slash through the epsilon. This seems so simple, and as we shall see, leads to so many difficulties. The concept of unambiguous rule means that given any object which you can experience or imagine, the rule will tell whether or not that object belongs to the given set. Here are some simple examples of the types of set which occur in mathematics. The set A consisting of the 3 natural numbers 2, 3, and 7. This can be described by simply listing the numbers. The set B of integers -11, -2, 5, and 13, which again is best described by just listing its members. Then consider the set D of all natural numbers which do not lie in the set A. So D would be the set of numbers x, such that x belongs to n, the natural numbers, but x is not equal to 2, x is not equal to 3, and x is not equal to 7. We have a special name and notation for this set D, which is defined as all objects in our universe which are not members of A. D is called the complement of A and is denoted by a superscript C on A. Now let's turn to some examples of sets of real numbers. An interval on the real line is a set of all numbers between a given number a and a given number b, with a less than b. The set of all numbers strictly greater than -2 and strictly less than 4 is an interval. This is called the open interval between -2 and 4 because it does not contain its endpoints, and it is denoted with parentheses. Left parenthesis -2, comma, 4, right parenthesis designates all numbers strictly between -2 and 4. We have no problem deciding that the number -0.2 does belong to this interval, while the number 4.0001 does not belong to this interval. So the rule is certainly unambiguous. Given any number you can imagine or experience, you can tell if the number belongs to this interval. There can be problems in this simple case, however. Does every x satisfying the polynomial equation x to the 10th minus 2x cubed plus 4 equals 0 belong to this set? The problem here is not in the definition of the set. The problem lies with determining the solutions of that equation, which is a problem for the numerical folks, not the set theorists. In general, given two numbers with a less than b, the open interval ab is defined as all numbers strictly between a and b. It can be sketched with open circles around the endpoints to show that they don't belong. An open interval has a very important and not at all obvious property, which is actually a modern characterization of openness. First of all, let's define a neighborhood of a point C on the real line to be any open interval containing the point C. For example, if C is 2, then all of the following are neighborhoods of C. N1, the open interval from 1.9 to 2.3, certainly contains 2 and is certainly an open interval. N2, the huge interval from -10 to +101. And N3, the open interval from 1.9999 to 2.00001, is still an open interval and still contains the point 2. Of course, in general, we are thinking of a neighborhood as a very small open interval centered on the point C. Now consider the open interval -2 to 4. I claim that given any point inside this interval, there is some neighborhood of that point which lies entirely inside the interval, i.e., it doesn't stick out into the complement of the interval. For example, if you choose the point c equal 1 inside the open interval -2 to 4, then you have lots of room to place an open interval about that point c equal 1 and not stick out. For example, you could choose the interval 0, 2. Now, if you get a bit nasty and choose something close to an endpoint, for example, choose c equal 3.9999, I can still place a very small open interval about c which does not stick out. For example, 3.9998 up to 3.99991 will do very nicely. If an interval contains both of its endpoints, we say it is closed, and we denote that with square brackets rather than parentheses. If the interval contains one endpoint but not the other, we say it is half open and use a square bracket for the endpoint which belongs, and a parenthesis for the endpoint which does not belong. All of these examples are easy to sketch. We use an open circle for an endpoint which does not belong, and a shaded circle for an endpoint which does belong. We can also describe unbounded intervals on the real line. For example, the set of x greater than or equal to -1 would be written as bracket -1, comma, infinity symbol, parenthesis, a half open interval. And the set of points to the left of 4 would be designated parenthesis minus infinity, comma, 4, right parenthesis, an open interval. In all of these examples, the universe was the real numbers R. The universe is in general obvious from the context, but it is important. For example, if our universe is the natural numbers n, then the set of natural numbers between 1 and 10 is no longer a half-open interval. It's just a list of natural numbers from 1 through 9. It is not easy to sketch more sophisticated examples. For example, try sketching all the irrationals. Or try sketching all numbers whose decimal expansion does not contain a 6 in the first 100 terms. These are perfectly valid sets, but we can't draw any kind of picture. Now we can also define sets in the Cartesian plane. For example, consider the set A, which consists of points whose coordinates x, y are such that x lies in the open interval between 1 and 2, and y lies in the open interval between 2 and 4. This defines a rectangle in the plane. This rectangle does not contain any points of its boundary. Notice that this means if we are at any point in the rectangle, there is a small circle about this point which is entirely contained within the rectangle and does not stick out. If you choose a point C close to the boundary, then the circle must be small. The closer C is to the boundary, the smaller the circle must be. In fact, this is how an open set is defined in the plane. Just as we defined a neighborhood of a point C on the real line as an open interval containing C, we define a neighborhood of a point C with coordinates PQ in the plane as any disk centered on C, defined by strict inequality. The disk must be defined by strict inequality, just as an open interval is defined by strict inequalities. Then an open set is defined as follows. A set A in the plane is open if for any point C in the set, there is a neighborhood of C which lies entirely in the set. For example, consider the set A consisting of points with coordinates x, y, with x in the half-open interval between 1 and 2, including the point 1, and y in the open interval between 2 and 4. This set is not open. The point C with coordinates 1, 3 belongs to A, but any disk about C sticks out into the complement of A. This is as far as we need to go for now with the theory of neighborhoods in open sets. I want to return to a discussion of set theory in general to finish off. There is a wonderful algebra of set theory, which was developed to a large extent independently by George Boole and Augustus de Morgan over the period 1840 to 1870. In the same way that Descartes introduced symbolic manipulation into geometry with his invention of analytic geometry, Boole and De Morgan introduced symbolic manipulation into mathematical logic and set theory. The algebra of sets is based on the idea that you have a universe denoted by U, from which you choose your sets, and you can carry out the following operation. First of all, the union of a set A and a set B consists of all objects that belong to A or B or both. The union of A and B can be pictured by means of a Venn diagram. The second operation on sets is the intersection of a set A and a set B. The intersection of A and B is a collection of all objects that belong to both A and B with an associated Venn diagram. Then we have the complement of a set A. A complement is the set of objects in the universe that don't belong to A and has a very simple Venn diagram. Finally, given two sets A and B, we can form the Cartesian product of A and B. A cross B is the set of all ordered pairs PQ, where the first object in the ordered pair, P, comes from the set A, and the second object in the ordered pair comes from the set B. This last operation is used to form the Cartesian plane of ordered pairs of real numbers. One way to think of that plane is to take the Cartesian product of the real line with itself. That would, of course, be R cross R, which consists of all pairs xy with x in R and y in R. In addition, the algebra of sets has an analog of the number 0, namely the empty set denoted by an O with a slash through it. This represents the set with no members. It's easy to see that A union the empty set is equal to A for any set A, similarly to the fact that if you add 0 to any number, you get the number back. There's also an analog of the number 1, namely the universe U. Since A intersect U equals A for any set A, this is similar to the fact that x times 1 equals x for any number x. In analogy with inequalities between numbers, we have set inclusion. A contained in B means if x belongs to A, then x belongs to B. And it has a simple Venn diagram. And yes, we can allow for strict inequality of the two sets. That is, we say that A is a proper subset of B if there are elements of B not in A, and we write A contained in B without the line under the contained in symbol. Here are some examples. Let the universe be the integers, and within that universe define the following sets. A will be the 4 natural numbers 3, 6, 8, and 11. B will be the 4 natural numbers 2, 6, 8, and 12. And C will be the 4 natural numbers -2, 4, 5, and 13. Then A union B is the list of numbers 2, 3, 6, 8, 11, 12. The list of all numbers that belong to either A or B or both. A union C is a longer list, as you can see, and B union C is an even longer list. A intersect B. Well, we look at A and we look at B, and they only have 2 numbers in common, 6 and 8, and that's the intersection. A intersect C is the empty set. They have no numbers in common. B intersect C is also the empty set. They have no numbers in common. The complement of A is all the integers except for the numbers that are listed in A, 3, 6, 8, and 11. B complement is similarly defined as all integers except for the numbers 2, 6, 8, and 12, and similarly for the complement of C. Finally, the Cartesian product of A and B is surprisingly long to write out. You have to take the first element in A, that's the number 3, and you have to pair it with each successive element of B. So you get the pairs 3, 2, 3, 6, 3, 8, 3, 12. And that's just your first step. Your second step is to take the second element of A, the number 6, and pair it in turn with each individual element of B, including 6. So you get the pair 6, 6. And then you do the same thing for the third element of A, 8, and the fourth element of A, 11. The first thing that De Morgan and Boole noticed was that the laws for these operations are very much like the laws of arithmetic. In particular, both union and intersection are commutative and associative. Commutativity states that the union of A and B, that's A union B, is the same as B union A. It doesn't matter in which order you write the two sets. And the same is true of the intersection. A intersect B and B intersect A gives you exactly the same result. Associativity says that if you have the union of 3 sets, for example, A union B union C, well, you can only do union 2 at a time. So you have to associate or group the sets into pairs. So for example, for the union of A and B and C, you might first take A union B, form that new set, and then take the union with C. Or you might take B union C, and then take the union of that set with A. Associativity states that you don't need to worry about this. Either procedure will give you exactly the same result. And the same is true for intersection. It doesn't matter how you group the terms 2 at a time, you always end up with the same result. Finally, we have a result for complements. If you take the complement of A, that's everything outside of A, then you take the complement of that set, you get A back. That is, A complement returns the set A. Venn diagrams make these properties intuitively obvious. However, a genuine proof requires that we show the two sets are equal using only the definitions and logically acceptable arguments. In a first course, this is too much of a rather dry digression, so we will accept the intuitive results from the Venn diagrams. Now, from these elementary properties, De Morgan discovered his famous laws. There are, in fact, two laws. The first one states that if you take A union B and form the complement of that union, you get exactly the same set as if you took the intersection of A complement and B complement. An intuitive way to think of this is that when you have A union B, that set complemented, the complement symbol drifts across, hits A, hits B, and flips the cup into a cap, the union into an intersection. And the same kind of result holds for intersection. If you take A intersect B and take the complement of that set, that's the same as the union of A complement and B complement. Again, a Venn diagram makes these assertions intuitively obvious. A complete rigorous proof is in the text for our course. The work of Boole and De Morgan was pretty much ignored except among logicians and seemed to have no practical use. In the 1930s, a young student named Claude Shannon attended a philosophy class at the University of Michigan that introduced him to Boole's work. Shannon went on to write a master's thesis at the Massachusetts Institute of Technology. And in that master's thesis, he showed how Boolean algebra could optimize the design of systems of electromechanical relays that were then used in telephone routing switches. He also proved that circuits with relays could be used to solve Boolean algebra problems. Employing the properties of electrical switches to do logic is the basic concept that underlies all modern electronic digital computers. Hence, Boolean algebra became the foundation of practical digital circuit design, and De Morgan and Boole via Shannon are credited with providing the theoretical foundation for our digital age. The rules of set theory we have been discussing are still of considerable use in the design of electronic circuits, where union means two switches in parallel and intersection stands for two switches in series. Complement means to change a switch's status to closed if it's open, to open if it's closed. The introduction of the algebra of sets into circuits theory got its first big success when Claude Shannon was working at the Bell Telephone Laboratories in the 1950s. Engineers were understandably resistant to something that looked so unapplied, until an engineer who'd been trained in the new algebra used pencil and paper to design a coding circuit in under 3 hours, with a substantial reduction from the number of switches required. The original design group had worked for several days to come up with their inferior design.